Hello students. Welcome to Varun Tutorials. In this video, we will learn about electrical circuits and how to formulate their governing differential equations. We will study resistance, inductance, and capacitance voltage drops, state Kirchhoff's voltage law, and solve practical circuit examples step by step. Let's study electrical circuits. We will consider circuits made up of the following basic electrical components. First, a voltage source, represented by E, which may be a battery or a generator. Second, passive elements, resistance, inductance, and capacitance. Let I be the current flowing in the circuit and Q be the charge on the condenser plate at any time t. Then, current I is the derivative of charge, dQ by dt, and charge Q is the integral of current I dt. Let's write down the voltage drops across each circuit element. The voltage drop across resistance is R times I, which can also be written as R times dQ by dt. The voltage drop across inductance is L times di by dt, or L times the second derivative of Q with respect to t. The voltage drop across capacitance is Q divided by C. We apply Kirchhoff's voltage law to write the governing loop equation. The law states that the algebraic sum of the voltage drops in each part of any closed electrical circuit is equal to the resultant electromotive force, or EMF E, applied in that circuit. Therefore, the governing differential equation for a series circuit is L times di by dt plus R times I plus Q over C equals E. Let's solve the first example. If a voltage of 20 cos 5t is applied to a series circuit consisting of a 10 ohm resistor and a 2 Henry inductor, determine the current at any time t, assuming the initial current is 0. Let I be the current flowing in the circuit at any time t. We write down our given parameters. The input voltage E is 20 cos 5t, resistance R is 10 ohms, and inductance L is 2 Henrys, with the initial condition that current is 0 at time t equals 0. By Kirchhoff's voltage law, the sum of voltage drops in the closed loop must equal the electromotive force. This gives L di by dt plus R times I equals E. Substituting our values gives 2 di by dt plus 10 I equals 20 cos 5t. We divide both sides by 2 to write it in the standard first-order linear differential form. This yields di by dt plus 5I equals 10 cos 5t. We label this as equation 1. This equation is of the standard form, di by dt plus p times I equals q. By comparing terms, we identify that p is equal to 5, and q is equal to 10 cos 5t. We compute the integrating factor, if equals e raised to the power of the integral of p dt, which is e to the power of 5t. The general solution of a linear equation is, I times the integrating factor equals the integral of q times the integrating factor plus a constant c. Substituting our values gives I times e to the power of 5t equals the integral of 10 cos 5t times e to the power of 5t dt, plus c. We factor out the constant 10. Let's recall the standard integration formula for the product of an exponential and a cosine function. The formula states that the integral of e to the at times cosine bt is e to the at over a squared plus b squared, times the quantity a cosine bt plus b sine bt. Let's apply this integration formula with parameters at equals 5 and b equals 5. The integral of e to the 5t cosine 5t dt is equal to e to the 5t over 5 squared plus 5 squared, times the quantity 5 cosine 5t plus 5 sine 5t. Simplifying the denominator gives 50. We also factor out 5 from the brackets, giving 5 over 50 times e to the 5t times the sum of cosine 5t and sine 5t. Reducing the fraction, 5 over 50 simplifies to 1/10, so the integral is e to the 5t over 10 times the sum of cosine 5t and sine 5t. Now we multiply by 10 to find the full integral from our general solution. Multiplying by 10 cancels out the denominator of 10, leaving exactly e to the 5t times the quantity cosine 5t plus sine 5t. We substitute this result back into our general solution equation. This gives I times e to the power of 5t equals e to the power of 5t times the quantity cosine 5t plus sine 5t, plus c. To solve for current I, we divide both sides of the equation by e to the power of 5t. This yields the general solution, I equals cosine 5t plus sine 5t, plus c times e to the power of minus 5t. We label this as equation 2. Next, we apply our initial condition, at t equals 0, current I is 0. Substituting t equals 0 and I equals 0 into equation 2, we get 0 equals cosine 0 plus sine 0 plus c. Since cosine 0 is 1 and sine 0 is 0, this simplifies to 0 equals 1 plus c, which gives c equals minus 1. Substituting c equals minus 1 back into equation 2, we obtain the final current function, I equals cosine 5t plus sine 5t, minus e to the power of minus 5t. Let's solve the second example. A circuit has in series an electromotive force given by E equals 100 sin 40 t volts, a resistor of 10 ohms, and an inductor of 0.5 henries. If the initial current is 0, find the current at time t. Let I denote the current in amperes flowing through the circuit at any time t. The given parameters are, voltage E equals 100 sin 40 t, resistance R is 10 ohms, and inductance L is 0.5 henries. The initial current at time t equals 0 is 0. The voltage drop across the resistor is R times I, which evaluates to 10I. The voltage drop across the inductor is L times di by dt, which is 0.5 di by dt, or 1/2 di by dt. Now we apply Kirchhoff's voltage law to formulate the loop differential equation. Summing the voltage drops gives 1/2 di by dt plus 10I equals 100 sin 40 t. Multiplying the entire equation by 2, we obtain the standard form, di by dt plus 20I equals 200 sin 40 t. We label this as equation 1. This is a linear differential equation of the first order form, di by dt plus p times I equals q. Comparing terms, we find p is equal to 20, and q is equal to 200 sin 40 t. We calculate the integrating factor, f equals e raised to the power of the integral of 20 dt, which simplifies to e to the power of 20 t. The general solution of a linear equation is, I times the integrating factor equals the integral of q times the integrating factor plus a constant c. Substituting our variables, we get I times e to the power. Thank you for watching. If you found this helpful, please like, share, and subscribe to Varun Tutorials. Turn on notifications so you never miss a new video.